My name is Danielle Dean. I'm a senior data scientist lead at Microsoft. I work in the algorithms and data science group, working with customers and partners, building out solutions using data science and machine learning.
Hey, good morning, everyone. My name is Wee Hyong. I'm a senior data scientist lead as well at Microsoft, same group as Daniel. And the reason why we put together this talk is essentially having a gathering of all of us in this room as superheroes. And that's why we're in the superheroes t-shirt, right? And hopefully we can learn from each other, right? Each superhero has their unique powers. We don't claim that we know all of them. And that hopefully by the end of this session, we have a good interaction. And if you are in the room and you have a phone and you want to tweet, feel free to tweet what is your data science superpower and tell us about your data science superpower, right? Now, this is an evolving set of talks that we've been giving. And the point here is whether you're a data scientist or whether you're an aspiring data scientist, I think it's important for us to be able to share with the community, right? What makes you really successful? And hopefully this talk is just the beginning, right? And we will be able to then learn from each other, right, and evolve. Now, so before we start, let's just have a show of hands. How many of you in this room are superheroes? Oh, wow.
Oh, yeah.
No, that's not our usual question. How many of you in this room are data scientists? Just to get a sense? OK. How many of you are aspiring data scientists? Awesome. Thank you. And how many of you are just here either because you want to learn about superheroes, right, or you are interested to learn about what kind of skill sets do you need in order to work with data scientists? Awesome. Good. So let's get started. So just before we get into the superpowers, I thought it's apt for us to be able to share, hey, you know what is data science? Now, for many of you who are really seasoned data scientists, this would be very familiar to many of you, right, where data science itself is not just a specific field, right? It's a multidisciplinary field, right? And whether you're in computer science, whether you're in math and statistics, or whether you're just a subject matter expert, every one of us have a role to play in either helping data scientists or in the field of data science. And the point here is we've always been trying to find what is in the center. Someone, right? Somewhere inside you, you think you have all this skill set, and therefore you deserve a higher pay kind of thing. But what we're trying to get to is maybe unicorns do exist, or they do not exist, but superheroes do exist, right? We've been growing up since young, watching a lot of superhero movies. Just 2 nights ago, I was watching Batman, just to get used to this talk, right? Getting into the superhero mentality. But the point here is we believe that in each and every one of you, right, superhero do exist. And that's what makes you effective in work every day, and that's what makes you effective in doing data science, right? Now, and many a times when you're at the hallway at work or you meet someone at this conference, you are always very shy to go up to someone to say, hey, you know, what is your secret? And maybe that person is not going to tell you because it's their trade secret kind of thing. But hopefully with this, you'll open up a forum for you to have that discussion. Now, just to make sure that if you are not in this field, you get a sense of the different terminologies that we might use throughout the presentation, starting with training data. Many a times when you do data science or you work with data scientists, you'll hear them asking, hey, you know, can I have training data, right? And to those that's not from this field, right, if you're a database guy or you're a database professional, right, this could be data sitting in a relational table, which you can do a select star, right? Or if you're just a subject matter expert, the training data could be data that's just sitting in your Excel file, right, waiting for insights to be discovered. And then, of course, you hear data scientists. When I first, I'm not a data scientist by training. I came in halfway. And then many times people tell me, hey, you know, tell me what are the features, right? And because I come from a database system background, features to me are just columns in the tables, right? And sometimes this two group just doesn't talk. And I say, oh, no, I have no features. I just have columns in the table. And then you see two of them in a very passionate kind of discussion, arguing what are features and columns. They are the same thing, right? Now, and often you also hear people asking, hey, now that you have training data, you have identified your features, right? And if it's a classification kind of problem, what is your target or what is your label, right? And essentially, it's just one column that tells you what you want to predict, right? And of course, it's one column in your training data that tells you what has already happened so that you can train on it, right? And then you often hear a lot of discussion to say, oh, what is a learner, right? Well, today you can just treat a learner as just a machine learning algorithm. It could be a classification algorithm. It could be a regression algorithm, right? It could be a time series algorithm, right? Now, and then, of course, there's also this part that talks about feature engineering, which we'll cover a lot, or munging or data wrangling, right? And you hear all these terms coming to you at all these conferences. Sometimes you know some of these terms and not the other. Now, what this simply means is simply getting data from wherever sources that you acquired from into the right shape, right? So that you can feed it into one of your learners or your algorithms, and then they can do wonderful things. Now, the last piece which we'll cover is essentially this concept of parameter and hyperparameters, right? And you'll see this throughout this talk as well, and we'll illustrate it with examples. So let's get started. Now, we thought it would be very interesting to say, well, we are talking about what is a data science superpower kind of talk. But why should you believe me or Daniel, right? We are not the best data scientists in the world. We're still learning. And we thought it would be apt to say, well, before we start looking at all the different superpowers, to invite one of the customers, Kensai, right, James from Kensai, to be on stage. And I'll let him introduce himself, to share with you stories from the trenches, stories from one of the very exciting projects that he's working with, right? And hopefully with that, when we get to the data science superpower part of the talk, you will be able to appreciate why those data science superpowers are what they are, right? And why it will be useful to James. So I'll hand this over to James. Thank you.
Thank you. Thank you very much. Hi, I'm James. I'm a senior data scientist at Kensai. And we are fighting death with data science. We are a company that is going after predictions in quality of care. We're aiming to improve quality of care, reduce costs, and see better outcomes overall for patients in the healthcare system. We were incubated at the University of Washington through some research in various labs. We scaled in collaboration with Microsoft Ventures, a very wonderful program. Our team is it's a cooperation of physicians, so our subject matter experts, our data scientists, so our statisticians, our model trainers, and our developers. We're a very close, we're not a very siloed organization. On a daily basis, each one of these groups is all working together. So we're trying to be the center of that Venn diagram we looked at just a second ago. Our headquarters are in Seattle, and now we're here. So why are we looking at improving outcomes in healthcare? So if anybody that's been working in healthcare cost prediction may be familiar with some of these charts. In the United States, the per capita healthcare expenditures are one of the highest in the world, and yet we don't see the expected return on investment for that. So life expectancy in the U.S. is not where it should be, given the amount of money that we spend on healthcare costs. And given those costs, fraud in healthcare is costing us dearly. So 60%, so for context, 60% of all personal bankruptcies can be attributed to unpaid medical bills. And fraud, therefore, contributes to these costs. So 1% of healthcare costs can be attributed as loss to fraud. And fraud in the healthcare system is a very complex problem. So we see losses to fraud through improper coding. So diagnoses being improperly coded, price manipulation, using wrong diagnoses, billing customers that never receive services. And so this is a breakdown of some of the different levels of fraud. So fraud in healthcare can be as simple as a single claim being improperly billed. So at a claim level, a patient may have been billed for a procedure that they didn't receive, or potentially that procedure was priced unusually high given the quality of the care that they received. It can also go as high as being multi-party criminal conspiracies, where we see multiple providers or organizations cooperating with each other in order to manipulate prices. We attempt to attack each of these levels of fraud at Kensai. And the methods we use, if you're familiar, if you remember some of the slides earlier that Wihan showed, the methods that we use are fairly basic. So if you have any background in data science, you may recognize unsupervised learning, supervised learning. We treat fraud as a combination problem. So when we begin looking at a fraud cohort, we have a large amount of unlabeled data, which we look for irregularities in order to pinpoint fraud. And we create a feedback loop with our customers so that they can use that now labeled data in order to determine whether or not it truly was fraud, which we then use to improve our models. So our data science superpower is our ability to fight medical fraud. And how do we do this at an organizational level? So when we start a conversation with a customer, we don't start with the conversation of how much money do you want to save. We start with the conversation of how can we help you save more lives. And for our customers, saving more lives can be analogous to saving costs. More money means more money to spend on healthcare. So once we've started those engagements, one of the things that we see as being very beneficial is looking into ways that we can bring data scientists and business leaders at the company together. And we do this by making sure that we connect our data scientists, our developers, our claim specialists, our physicians. So really trying to make sure we are at the center of that Venn diagram, where we have engineering expertise, subject matter experts, developers, statisticians, all working together. And the way that we make sure that we're a catalyst for success is when we first start an engagement with a customer, we don't initially plan for a long-running marathon data science project where we're going to be spending months and months and months on a single problem. Rather, we break our projects, we break our deliverables into a pilot project that typically runs about 12 weeks. And for the individual frauds that we tackle, we allocate about 2 to 4 weeks for each fraud type, incrementally delivering additional savings for the customer. So at the beginning of the pilot, they will begin to see X amount of savings, which we then increase as we deliver more and more models for the customer. And then once all this modeling has been done, in order to make sure that we're connecting back with the decision makers at our customer, we leverage Microsoft products in order to make sure that these insights are consumable by business decision makers. So if you look on the left side of the screen, this is how we are exposing one of our fraud models. So one of our fraud models being a distance-based rules as to which patients we expect to be going to which doctors. And so what we're showing right here is that for a patient at the red node, which doctors have the highest probability of having fraudulent visits. The logic being that you travel further, you are less likely to travel further to go see your doctor. It's something that's we've found to be fairly useful. Our architecture, I'll go over really quick. So the types of data that we are consuming, we're consuming EMR data, electronic medical record data, claims data, admin and finance data, as well as patient-generated data. So you have your Microsoft band, and if we're able to have access to that, we'll leverage it in our models. We go through an ingestion phase where we take in all these data sources from our customers. We impute missing values and we coerce it to a standard schema that we have that we use for all of our models. And then we have a scoring network of many different models. So for each of those, so just for fraud alone, we have many different models scoring many different types of fraud that are each feeding off of this common schema that we have. And in order to do all this, we're leveraging Azure Data Factory and Data Catalog in order to handle our movement and our registration of data sources. The outputs of all these models then feed into these apps. So for example, the one that I showed earlier around distance, that's an example of one of the apps that our models feed into. We can then layer additional apps on top of this. So for a different type of fraud, a map might not be the best way to visualize it. So we create additional apps for the customer to consume these the results of these different types of fraud models. And we finally expose all the solutions through a series of APIs and through the apps that I just mentioned. And now, before I wrap up, I'd just like to go to a quote from one of our major customers. They're a leading healthcare provider in Asia, covering 9 million lives. This was from an initial engagement we had with them. We had spent a very short amount of time and with them, and then within a few weeks, we're able to get the CIO of this company to say, and then boom, there's a few $100,000 worth of fraud identified within a few minutes. We did this on data that had been viewed by 20 of our claims specialists, and these were fraudulent transactions they didn't catch. Yeah, it's amazing. So that's our data science superpower. And with that, I'm going to turn it back over to Wei-Young. Thank you very much.
James. So let's get started to discover our superpowers. And what you hear from James is the following, right? Subject matter expertise, in this case, in the medical fraud, is super important. And later on, in one of the superpowers, you actually see how subject matter expertise is super important when you do feature engineering. And we'll get to it when we get to that part of the section. So let's discover our superpowers, right? Before we get started, well, this could be any one of us, right? Someone says, I'm a machine learning researcher. Someone says, I work on deep learning. I'm a data scientist. We got this photo from one of the events in Singapore. And we thought it was interesting because this is what superheroes are about. So let's get started with the superpowers. And just to frame the discussion, we broke superpowers, or we crystallized all these learnings from Kensai, from a lot of the other companies, as well as from data scientists that we talked to, right, into 5 superpowers. And we thought that this would provide a framework for us to evolve this further. And the first one is really being obsessed with data, right? I think it is super important to be obsessed with data for the following reason. Many a times when you get into a customer kind of discussion, they'll say, hey, I want to do data science. I want to do advanced analytics. Right? And the first question that you'll usually ask is, of course, you'll ask, hey, why do you want to solve this? Why is it important to your business? But once you get to the data science-y part of the discussion, you'll say, hey, give me some data so that we can see whether your existing data works. Right? And many a times when you get into a lot of this kind of conversations, the first set of data that they give you might not be sufficient, might be the wrong data. Right? Like for a while, I think just a year ago, Daniel and I was in Asia and in some of the countries in Asia. And someone was saying, hey, Daniel is the predictive maintenance expert. Come down to our building, and we're going to talk about predictive maintenance for HVAC data. Right? And when they gave us the data, it was highly aggregated. And it was not really data that we can work with or build a model with. Right? And as a data scientist, even though this seems to be such a simple, intuitive thing to say, hey, be obsessed with data, right? That ability for you to say, hey, if this data is not suitable for you in modeling, then you want to continue asking the right questions to a point where you have data and you think that you have sufficient data to do your initial modeling. Now, to illustrate this, let me just show you some examples. So this was one of the projects that we did a while back, sometime in June this year. And the point here is the following. Today, there is a huge database out there. It sits in SQL Server called the Sloan Digital Sky Survey. Right? It started by Professor Alexia, as well as Jim Gray from Microsoft Research. That database itself is 12 terabytes loaded into a SQL Server instance. So sometime in May, I think it's April, May this year, one of the leaders on our team say, hey, Wee Hyung, there's a data set. We need to be able to figure out how to build a model to classify galaxies into its different shapes. Get the data, right? And 12 terabytes, and we're thinking, hey, should I fly over to Johns Hopkins to get the data? Should we FTP? No, and of course, I put on the request to my boss, and my boss said, well, do FTP first, right? Cost savings. And we did. We actually FTP'd the data over 2 days. Even though it's 12 terabytes, when it's a compressed SQL Server backup, it's 6 terabytes. 2 days, we actually downloaded the data, and my boss said, well, wow, you saved money for the company. Great job, right? Now, then the next point is, well, now that you have the data, this is a huge database, right? There are specific things in the data that matters to us in order to be able to build a galaxy classification model, right? And some of the data scientists on our team work on that. But the point there is not all of this data can be used, right? And the second thing is, many a times, especially for data of this kind of scale and of this kind of type, we might not have the subject matter expertise. That's the reason why we talk about Kensai having deep expertise in medical fraud. And we realized that, hey, all this data to us are just values. We could treat them as just numerical values and then build a model, right? Naturally, the model is not going to be great, right? So it's a constant question on, hey, can we do feature engineering? Can we get more features? Or can we get a subject matter expert into this? And it turns out that Microsoft is a really amazing place. I say that not because I'm in Microsoft, but it's really an amazing place to be in. And it turns out that some folks on our team has a PhD in astronomy, and he actually discovered a quasar, right? And we say, well, great. So with the subject matter expert working with one of the data scientists from our team, we built a model, right, to classify galaxies. And to show you that, let me just show you this demo from machine number 8. Can we switch to the demo screen? Now, this was the app that was built in order to illustrate this concept, right? And what you're seeing here, you actually get an equivalent if you search for the Worldwide Telescope, right? This is a modified version of the Worldwide Telescope to illustrate some of these ideas. And back end, this is really powered by the database that's 12 terabytes, right? And I could do things like search, and I could say, well, let me look for blue shifted objects. Now, before the project, I know nothing about blue shifted objects. To me, they're just lights in the skies, right? And the moment I do search, you'll see that this comes back really quickly. It scans over a table of 1.2 billion rows, right? And this is really a very sparse table because it contains what astronomers call the photometric properties of objects in the sky, right? And because this was powered back-end by a SQL Server and with a lot of the innovations in the SQL Server space, we were able to optimize this query to run really, really fast, right? And of course, you could continue and say, hey, let's drill down and look at Messier 90. And this brings you to one of the galaxies. And then, of course, I could look at the properties of the galaxies, right? Now, but the point here is, for each of these galaxy pictures that gets taken by the Sloan Digital Sky Survey, it's important for us to be able to figure out what is the type of the galaxy. And simplistically, they have different kinds of type, whether it's a spiral galaxy or whether it's elliptical galaxy. Now, the interesting trivia from this is, as we seek to be obsessed with this data and being able to get to understand more of this data, either through a subject matter expert or by reading, we learn a lot of interesting stories about the data, so it benefits you as well. One of the things that we realized was that because being able to classify galaxies is such a huge and important thing to the astronomy community, right? A project was actually started called Galaxy Zoo, where they train citizen astronomers like many of us, right, to be able to do this work. The only problem is we will never be able to scale at millions of galaxies. And therefore, a project really got started to say, hey, can we use machine learning, right, to solve this problem? In fact, there was a Kaggle contest of a similar nature. And therefore, we did that. We went and we built a model, right, after we went through that whole exercise, right? And we said, well, if I want to do a random forest, immediately back end, right, it takes this new galaxy data with all the photometric properties. It sends it to SQL Server. SQL Server has a model that has been built that will score and say, well, this is spiral, this is elliptical, or this is unknown, right? And then it returns and we visualize it in the Worldwide Telescope. Now, of course, I could say, show me the cohort of the different galaxies, and you see star unknown, elliptical, spiral, and so on and so forth. Now, many times when we show this kind of example, you must be, looking at the screen that's right, and not looking on your phone. But you must be wondering, why am I telling you the story of a galaxy and doing galaxy classification? Now, look at this. This is cohorts of different galaxy shapes. Now, the same thing can happen to your customers, where you analyze the customer behavior, right? And then for you to being able to understand whether your customer is going to churn or whether your customer is not going to churn, or can do cohort analysis on your customers. So this is super important. Now, let's switch back to the slides. Let's switch back to the slides. Awesome. Now, and of course, we have many other examples. You might have seen the Rolls-Royce example. If not, it's a really interesting study on how Rolls-Royce reinvented the aircraft engine business, right? To a point where they say, hey, now that we've reinvented the aircraft engine business by not just selling engine, but selling airtime, right? Can we reinvent the business again through advanced analytics, right? And therefore, Daniel actually worked with Rolls-Royce, right, on a similar project on trying to figure out, hey, what is the remaining useful lifetime of an aircraft engine? And you can imagine the journey that she went through, right? How she started off with data that says, hey, these are just my aircraft engine data, right? And being continuously obsessed with the data to the point where she gets the data that she needs to do a modeling to finally a public case study that you see, right? And we hear stories all around. This is recent work done by some of the folks from our Boston team, right? That shows how you could use deep neural networks, right, to be able to detect objects in a fridge, which eventually forms the basis for you to detect building smart refrigerators. And this is actually something that's close to many of our hearts as well, education, right? The ability to say, well, when a student gets into a school, we want to ensure that they do not drop out, right? And they will continue to become really successful in life. And this was a project that we worked with the Tacoma Public School, and we have a similar project in India as well, on using machine learning models to be able to detect whether the student has a potential to drop out. And this was actually really interesting because they thought, hey, what are the factors that contribute to students drop out? Now, the team that worked on this went through that journey, right? The same journey of saying, hey, let's just look at this problem, this specific school district, when the guy took over the job, he has a 53% dropout rate, right? And this is a huge problem, right? And us working with them to say, well, what is the data, right? How do you describe a student? How do you describe a student's journey through the educational system, right? And finally getting to a data set that led to this improvement or huge improvement in results. And the point that we're trying to get to in asking you to be obsessed with data is really getting from a vague kind of discussion to asking very precise questions, right? Many a times you'll see people say, hey, I want to do advanced analytics. I want to start an advanced analytics team and so on and so forth. But the point here is, why are you doing advanced analytics? What do you want to do, right? So you could say, well, I want to understand how many Model Z cars will I sell in Atlanta this month. I want to know which customers will likely churn, and so on and so forth. Now, leading that, let's move on to superpower number 2, and Daniel is going to cover that.
Thank you. So our superpower number 2 is data science is very nonlinear. You probably, if you're a data scientist, you want a lot more weeks to do many more iterations on the model, right? You got a model, you have more data. There's always so much more that you can do. But at the same time, we have to understand what is our end goal and how are we getting there. So I'm going to talk through in the next few slides what we think of as a linear method for nonlinear work. Now, of course, even in a linear process, it's not to say that we don't have to go back to previous steps. But if we actually have a defined process for how to approach problems, it can be very helpful to get to the solution. So here's an overview. If you get the slides from us later, we have lots of blog posts and series that describe this. So if you want to take a lot of this material and talk about the processes within your own teams, definitely feel free to leverage the material in the notes and the blog posts and so forth. So the data science process, our goal is obviously to solve a problem, to meet business goals through close collaboration. How that starts is starting with a data problem formulation. This, what Weiheng was mentioning, a very sharp question that we want to go after. We usually say that every one of these steps should actually have a defined document. So at step 1, we should have a defined scope of what we're trying to accomplish. This is usually from the business perspective, not from a data scientist perspective. What are we trying to accomplish? What are the goals? The next step is acquiring the data sources. This is figuring out what are those data sources that are needed, getting a hold of the domain experts, the subject matter expertise who can tell you what are the important data sources to solve that data problem formulation. Again, trying to end in some sort of document where you can say, these are the data sources that matter. Now, data science projects can stop after step 2, where you might say, hey, we don't have the data. We need to figure out a different data problem formulation. Because often in the case, you might not have the data you need in order to complete the whole process. But if you're doing a systematic process through it, you can at least identify where the gaps are, and that will help you understand and accelerate future proof of concepts. The next step is data exploration. This is really starting to understand the data. And Dr. Tufte gave a really nice presentation this morning about the importance of really understanding the data. Data are just numbers, but you need to understand where do those numbers come from? What do they represent? Who was entering those numbers? How did they enter those? Was there bias that people could have in entering those numbers? So my background's in predictive maintenance. I do a lot of work with customers in predictive maintenance. I had a talk yesterday that some of you might have been at. But this step of trying to figure out where that data came from is so important over all the different domains. In predictive maintenance, for example, you might have maintenance workers who are writing notes about what the problem was. Now, if different people are writing descriptions in different ways, that can really influence how you're going to analyze the results. So here, this data exploration phase, you're trying to understand how that data came about. The fourth step is creating the analytics data set. This is that feature engineering, munging, wrangling part where you want to take all of those different data sources, unstructured, structured, lots of different stuff, maybe at different levels, and combine them all together to create a final training data set that we can feed into a machine learning model. And that's the create the analytics data set step. The fifth part is modeling and descriptive analyses. This is where you're actually creating the machine learning model, trying to figure out if we can actually predict the outcome. That is the data problem formulation step. And then number 6 is the model evaluation and tuning. And this is trying to figure out how well is the model performing, and will it generalize to future data sets. And then the last step is the model deployment. And then we have also, during the same process, a data acquisition phase where throughout the whole process, you should be thinking about how you actually put these kind of solutions in production. Now, your process should not just be you, hopefully. Hopefully, you have a team around you because they have very different perspectives and different roles, and they play an integral part into a project. So, for example, a domain expert gives really valuable insight into how that data formed. The architect or engineer can help with the data collection, the processes behind how to put those into production, the data scientist to help with the modeling or data analyst, and then a project manager to help make sure that you're actually doing the process. Now, we actually have a team data science process. This has never been discussed before. So actually at a session from 3 to 5 today, we'll be talking about collaboration methods and what we're proposing to people as something that you can use in doing team data science process. So that's actually this afternoon from 3 to 5. So breaking news. I know the Twitter's going crazy, but actually a lot of people are taking pictures, so this is pretty cool. Whoever knew the process would be so cool. So team data science process today at 3 o'clock. So with that, we'll go to superpower number 3.
Now, superpower number 3 is really close to my heart, and I'm sure it's very close to many of your hearts as well, right? In order for you to get from a newbie data scientist to a point where you're productive and effective on a day-to-day basis, each and every one of us have a toolbox of tricks. Right? Tricks that allows you to get from data to a good model or to a good baseline model really quickly. Right? And today we're going to just share a few of them, and hopefully we'll evolve this toolbox together. Now, just before we get into some of these tricks, I thought this quote was particularly relevant for this talk is, well, while we could continue advancing the state of many machine learning algorithms, and we should continue to do it, many a times, given data that you have, and you've gone through the whole process of getting a subject matter expert, right, being obsessed with data, getting to a point where you're ready to model, sometimes your original data might not have all the features that you need, right? And therefore, feature engineering, when I first joined this field, I never understood how important it is. It is really super important because it's going to differentiate you from getting from an initial model to a really good model, right? And therefore, better features are actually better than better algorithms. Now, one of the funny things that came to me as I get into this field of data science is, many a times when we want to get into data science, what do? The first thing is you search, how do I get into data science? And you see a huge amount of courses out there. First thing that is back of your mind is, which one should I take, right? You search for books on Amazon and a bunch of other websites. You go down to the public library, and you say, which book should I start reading, right? There is tons of materials in data science. And suppose you take a course, right? For example, UW has a Master's of Data Science as well as a Certificate in Data Science kind of courses. And you take a course. The course has a capstone project. And not just specific to UW, but a lot of the universities, both in US, in Asia, and Europe. And the capstone project sometimes asks you to work on Kaggle contests, great, right? But a lot of the classroom examples will always start with a tutorial data set, right? It's super important to start with that tutorial data set because it helps you understand and internalize the concepts. But the point is, well, after you finish this, you have that certificate, or you have a master's in data science, you find a job as a data scientist, assuming you're doing a mid-career change. And the first thing, suppose you get the job as a data scientist, and the first thing on your first day or first week of job is, well, now you are a data scientist, we want you to solve a real-world problem. And you suffer from this problem of getting from a tutorial data set, which we call the not-so-real-world data set, to an actual data set. And all kinds of things happen. I'm sure every one of you have that kind of experience, right? Your model was just horrible. No matter how hard you tune it, it just doesn't improve, right? And over this time, of course, your toolbox of tricks will come and help you, right? So one common thing in all this data set, like before I joined Microsoft, I used to work in telco in Asia. And one of the things that we had is we have to figure out customer attrition or customer churn, right? Then, of course, you could get data from your data warehouse. You could get it from different sources. And you want to build a model. But what you realize is that this is very interesting because there are some specific characteristics of all these data sets that make this data set challenging, which does not exist in your tutorial data set. Anyone has a sense of what it is? Sorry? Okay. Sorry? Okay. Outlier, okay, thank you. Any other? Unstructured data, that's great, thank you. Class imbalance, thank you. Yes, so all these are all problems that will possibly exist in this data set, but class imbalance is really one of them. And the point here is, if a telco has lots of customers that are churning, meaning they could be downgrading to a lower level service or they're moving to another provider, and these days with number portability, it's really easy to do it, then if you try to train on this, you realize you have a problem. You train on the so-called majority class, but the point is the business wants to figure out which are customers that's going to churn, right? Because then you can address specific programs for them. Now, similarly, if you have aircraft engine failure, right? Like, for example, when Daniel worked with some of the airlines in the world, right? You get data, and if this airline gives you a data set that has huge amount of aircraft engine failure, I'll probably not take the aircraft from the airline, right? And failures are rare, but these are always the important thing that you want to train on because these are the things that the business is genuinely interested in because it helps them alleviate a lot of the later problem. In this case, it could be a life and death situation, right? And when you have class imbalance, which is a term, thank you for the sharing, right? How do you go about solving it? And as we were saying, learners are biased naturally towards majority class, right? And therefore, the problem is minority classes. In this case, it could be churn, it could be aircraft failure, aircraft engine failure, tend to be misclassified. Now, when I first came into my job, I performed horribly, right? I probably got a really bad review because when I did my tutorial data set, I didn't come across this problem, right? I could blame it on my teacher, right? Or I could blame it on the books I read, but then it is still a problem. And it turns out that there's really a lot of ways of solving this. Yesterday at the keynote, you saw one of the companies solving class imbalance problem in the context of drones and monitoring by generating synthetic images. Right? That's a very creative way of solving a class imbalance problem for data that's not structured. But in this case, it turns out that if you have structured data, there is actually a technique called SMOTE, called synthetic minority oversampling technique. Right? I'm not saying that this is the answer to all your class imbalance problem, but starting with SMOTE, and SMOTE is available in whether it's in R, in Python, or in Azure Machine Learning, you can leverage it, and immediately you have a very effective way, right, to solve your class imbalance problem, right? And that might get you to an initial good result, right? Now, the other thing to take note of, just as a small fine print, is that the SMOTE implementation in Azure Machine Learning and what you get from an R library, there are slight differences. So if you do use SMOTE, you will have to make sure that all your parameters are set correctly, right? Now, the next thing, which is also very common, right, whether you're in class or whether you're on the job as a data scientist, is you ask yourself, why am I doing so many iterations of trial and error? You start off with a model, you choose a right algorithm to use, and you realize that the results is not good because you evaluated it against the testing data. And what do? If it's a random forest, you might be saying, hey, I am going to change the number of trees. Or I might change the number of minimum samples I need in my leaf nodes. Right? And similarly, for a lot of the other algorithms, you might be tuning the different parameters. The question is, why am I doing so many iterations of trial and error? And someday I get lucky, I get to a good result. But is that the right way? Or is there a more effective way of doing it? Right? And it turns out that, well, a simplest approach is for any kind of learners that you have, right? And you have a bunch of things that you want to tune, you try all possible methods, right? And Azure Machine Learning actually provides you with great ways of doing it. But the problem is, you want to get to a point where someone gave you a data, you've gone through the whole process of doing feature engineering, and you're ready to build the model. And you say, well, I want to exhaustively or brute force search over the search space of all possible combinations so I get a good result. It's not possible because it might take hours, it might take days, it might take weeks. Right? But it's always important to do fast experimentation. And therefore, you want a smart way to be able to do it, yet ensure that the results that you get from an algorithm that runs at a shorter time frame still is close to the good results that you're expecting. Right? And it turns out that this is an interesting problem. You could either select parameters randomly, or you could have a smart way of picking parameters. Right? And it turns out that if you have a random grid and you choose 59 random points from the parameter grid, it will actually guarantee you with a 95% confidence that top 5% of the accuracy will be obtained. And what this simply means, and you have a paper from the previous section, is yes, it's important for you to be able to search through the grid, but maybe you could reduce the search space. Your tuning runs faster. You are assured that the results that you get is of a reasonable, or is reasonably close to the final results, good results that you're expecting. And it turns out that Azure Machine Learning do have a hyperparameter module. So let me show you. Let me switch to the demo screen again. So let's quickly, in a very short amount of time, build an experiment. So if you have not seen Azure Machine Learning, this is the Azure Machine Learning Studio. Right, I could say, well, I want to use a very standard data set, which I call the adult census data set. And I say, well, I want to split the data. You realize that I'm not doing any feature engineering, more from an illustration purpose. I want to train my model. I want to score my model. I want to evaluate my model. And then I'm going to connect all this up. And then, of course, now I will choose an algorithm. So I could say, hey, I want to do a 2-class classification. You have a bunch of them to choose from. Let's suppose I take a decision forest. I connect everything up together. Right, I want to predict what is your income. The screen is very small. Let me just make sure my screen is smaller. Oh, where's my... And I choose income. And so at this point in time, this could be an experiment that you create. Of course, in a real-world kind of project, this experiment could be more complicated. But essentially, you chose an algorithm. You said that you want to train the model, and you're going to score the model against your test data set. Right? Now, and then, of course, you run. I'm not going to run this due to time constraint. And you'll get to a point where you say, hey, your results is not good. Right? In this case, it's a binary classification problem. Your AUC could be really low. What do? You go back to your 2-class decision forest, and you say, hey, my number of decision tree is 100. My maximum depth could be 50. It becomes that trial and error that I was telling you about. Right? And of course, you could say, well, maybe 2-class decision forest is not the right one. I want to use an MSR algorithm called 2-points based point machine. I'm going to copy the same thing. And you continue connecting all of this up. And yes, the Azure Machine Learning Studio provides you with a great way to do this kind of experimentation really quickly. But again, I have to go to the base point machine and to say, hey, what is the number of training iterations? It is continuous trial and error, and sometimes that can be frustrating, especially when you have a project deadline. Right? Now, that hyperparameter tuning that I was telling you is a module, so you could say hyperparameter tuning. Tune model hyperparameter. All I need to do is to replace the trained model, bring in the hyperparameter tuning, connect everything nicely together. And of course, I have to say, hey, what do you want to train on? I'm going to train on predicting the income. And once I'm done, you'll realize that I have a matrix for measuring performance, and I can choose what do I want. Do I want to optimize for AUC, F-score, and so on and so forth? Now, the moment I run this, then it will always, you'll go through the similar trial and error that you have, but in a really smart way. You start this, it might run for a while if you have a lot of iterations. Go for a good lunch, come back, you get wonderful results. Right? Now, the point here is also the following. You realize that you can control the number of iterations, and you can say whether it's random sweep or random grid, which relates to the idea I was telling you earlier. Now, let's quickly get back to slides. And of course, there's other kinds of methods, and I'm going to go through. Right, and you already saw the demo. That's great. Now, the question is, are there tips and tricks that enable you to get to a good initial baseline? Right? That's something that all of us are striving to work towards on. Now, it turns out that for some of this problem, like churn, yes. So this was KDD Cup 2015, 8 million rows, 7 column. It was the exact problem of predicting customer churn for an online course. Now, KDD Cup itself, first challenge is, how do you build an initial experiment that's within the first 1% accuracy of the winning solution? 2, how do you build an initial experiment that's within the top 30 without you doing anything? You think that is possible? Anyone? Oh, wow. Now, it turns out that this is not a concept that is new, right? It has existed for a long time, called RFM, right? If you're able to model this data set and identify what are the recency value, the frequency value, and the dollar value, right, which maps to have the student attended class recently, how many hours have the student spent on the course, how many problems has the student solved, and if you're able to get it into that kind of frame, then, just to put that into perspective, 800 entries for that KDD Cup, the winner AUC was 90.9, right? And that was after they merged 9 teams, the results from 9 teams, and over 250 iterations before they get to that. Now, using the RFM concept that I was sharing with you earlier, right, we got one of the data scientists on our team to do it, right, over a weekend, right? He modeled it as an RFM problem. He ran it in Azure Machine Learning. He did not do any tuning. right? He got an AUC of 90.1, and he was happy, right? The point here is with the right kind of modeling for the right kind of problems, it is possible to get to a good initial baseline, and we should continue striving it. So RFM is one technique that we're sharing. I'm sure you have your tips and tricks. Share with the community. We all learn from each other, right? Now, other kinds of toolbox, there's a lot of work on auto-featureization and so on and so forth. The question is, right, can we get to a point where we can auto-generate a machine learning model? It's like the holy grail, right? I start something, I give it data, and it runs, you go for lunch, you go for dinner, come back, oh, boss, I have a good model. Do you all think it's possible? Right, it turns out that there is one of the conferences called ICML, International Conference in Machine Learning. For the past 4 years, there's a workshop in this whole space of auto machine learning. There's some initial progress in that area, but there are works in that area as well, right? We should probably skip it, yeah.
Did you switch to the demo?
7, yeah. Should be 7.
Yep, I just did. Okay. Awesome. So if you guys go check out the Cortana Intelligence Gallery, there's an example experiment that does model selection for binary classification. So this is an example experiment where one of the data scientists put together, here you can see basically a lot of copy and paste, but we're trying lots of different algorithms and lots of scripts to pull it together and get the result out. So what we can do is, in this case, if your data already has all of the right feature engineering, which I'm not saying that this does, because as Weihong pointed out, you need to have that domain expertise, you need to try things like RFM analysis and so forth. But once your feature engineering is done, you can feed it into this kind of system and auto-select the best method for this binary classification problem, and then automatically deploy it as a web service API. So I won't go into more detail, but feel free to check out the gallery, and this is, again, is in our notes section. Can you switch back to the slides? I'll take that. Awesome, so I'm gonna go over superpower 4, which is learn from the experts and internalize. None of us know everything. There's so much out in the community. I think one of the coolest things about the data science community in general is all of the crazy different backgrounds that people have, oceanography, physics, chemistry. I come from quantitative psychology. So all of these different backgrounds can really provide lots of guidance and good ideas. So there's I just pointed out the Cortana Intelligence Gallery, gallery.cortanaintelligence.com, lots of material there to leverage. So definitely learn from the community. There's also some really awesome courses. So Microsoft now has a professional degree in data science that you can do. So this is all online. There's also lots of other, obviously, good material online from things like Coursera or edX. Here's another example, Data Science and Machine Learning Essentials. So this is a great class. Go back one. OK. So this is a Microsoft professional degree. And feel free to email us, too, if you want any of these materials. Microsoft professional degree, the edX course, and then I just have one more slide in this section, which is about how do I become a data scientist, for those of you who said you're aspiring data scientists. Our colleague Brandon Rohrer, he's out of Boston like myself, he has this awesome to-do list of how to become a data scientist. It has one item on it, which is literally start building stuff. So find out what you're passionate about. Maybe you want to pull some stuff from Twitter and do some kind of sentiment analysis about how awesome Danielle Dean is. You want to create some graphs. So figure out what you're passionate about, find a cool idea, and start building some apps. So that's really what we suggest on how to become a data scientist. And then last superpower, make insights actionable.
So the last superpower is actually close to many of our hearts as well, right? Make insights actionable. And what we mean by that is the following. You could be the best data scientist in the world, you build the best model, you have your toolbox of tricks, right? But if your insight stays as a model, and you are not able to get it into part of an automated system that's able to make decisions, right? Or you're not able to visualize your insights, then that model becomes just that model sitting in some of your laptop somewhere, right? It's not actionable. And as data scientists, I think we have both a responsibility to, of course, the organization that we work for, but as well as to the community to also share, right? Whatever good results that you have, right, you should be able to share. And you see that happening in a lot of the contests where if you're the top prize winner or top in the leader spot, everyone is actively sharing because only through that sharing we will improve. Right? And of course, from a business perspective, if you're able to get this insight into the hands of the business stakeholders, or to a point where systems or operational systems that happen in the retail stores consume the result of your model and being able to make more intelligent decisions, then your model is a good model, and your model is something that is useful to the business. Right? So making insights actionable is super important, and we're going to just share several different ways of making insights actionable. Now, before I get into that, let me just illustrate this with one example that you saw yesterday at the keynote. Right? Yesterday, you saw how we make use of Azure Data Lake plus cognitive services to analyze War and Peace. And trust me, War and Peace has been buzzing in my head for the past 1 month because of both the Data Science Summit and the Ignite keynote. Right? Now, War and Peace is a wonderful thing, and we saw how Matt Winkler was able to analyze it. And you saw that heat map, right? That heat map that tells you the romantic story of Natasha, right? And how she was happy, and by the time she got to a point where her family is bankrupt, right? She goes through some trials and tribulations in life, right? How do we go about reading a book using data science? So let's switch to the demo machine. So this is peeling under the hood at what you saw at the keynote, specifically to that heat map. So what generated that heat map that you saw yesterday? Let me just open this up. This was the expansion of the heat map. Was Andre and Natasha went through that, right? They came together, and then eventually Natasha goes through some trials in life. And finally, towards the end, which is the first epilogue and the second epilogue of the book, right? She's happy again. And of course, you could continue drilling down on specific part of this, right? And continue drilling down, and so on and so forth. Now, this heat map is nothing fantastic. It turns out to be just one of the many visualization libraries that's out there. And I'm just going to show you how we built it. So we started off by reading or consuming the output from the analysis from Azure Data Lake called the epilogue key phrase. Now, how does this data look like? So if I go War, Peace, Free, it has the year, the book, the chapter, the text, and the results from the analysis, the sentiment score. Right? Now that we have that, all we did was to say, hey, these are the characters that we're interested in. And for each of the characters, let me try to group them together or try to assign them together. And finally, I get to a WP base. In this case, this just says, well, let me group them so that I have an additional column, which is character, which I'm going to group by later. So once I'm done with that, it becomes really simple. I continue to say, well, I want to resolve. It turns out that there are interesting characters in Russian literature, right, where all this resolved to Natasha. And I didn't learn that. We have a Russian data scientist on our team who is an expert in War and Peace because he went through that experience in high school, right? And then all this resolved to Pierre, all this resolved to Andre, and this resolved to Mary. And once we are done, we simply group characters and book, right? And because we need to feed it to a heat map, right, we modified or we did some transposing of the data, and finally we replaced the data value that are now, right, to be zeros. Once we are that, it's just a very simple way of just invoking D3 heat map, which could be one of the visualization libraries that you're already used to. And when I click run, this will then produce the heat map that you saw at the keynote, right, which is the heat map that I showed you earlier. Now, and let's get back to the slide. And this is just one way where we use data science to read a really amazing world literature, right? And trust me, now I can talk to you about War and Peace to some extent, which is great, right? Visualization and getting the result of your analysis to the hand of the end user and make it actionable is super, super powerful. Don't underestimate that. Now, if you're an aspiring data scientist in the audience, we see a lot of aspiring data scientists, in order for them to be able to contribute back to the community, writing really nice blog articles, either in GitHub or on their own blog sites, about a specific phenomena. It could be the accident data set. It could be data set about New York taxis, and they analyze, whether a celebrity paid a tip or not, which hotels they came from. They do wonderful visualization, super powerful, and that helps people, right, be able to tell a data science story, right? Now, but there are more ways to make insights actionable, especially within the organization. You could create dashboard, you could write a blog, you could operationalize a lot of the things that you do as a web service so that all your other web applications can consume it. You could publish your code on GitHub so that everyone can benefit from your work, right? Or you could, if you're using SQL Server 2016 with R, you could operationalize it as a stored procedure. And that has actually very profound impact. Why? Because you have a lot of line of business applications. A lot of this line of business application will not speak R, but they speak SQL, and they know how to invoke a stored procedure, right? And now with the ability to combine R into a stored procedure, all your existing line applications continue to work as they are, but they become more intelligent, which is super powerful. The point that we're trying to get to is moving from data to intelligent action, which simply means making it actionable. So the last piece, we end off with this slide. I'm obsessed with data. Hopefully, at the end of this talk, you have internalized a lot of this, and hopefully together, you will tell us what your superpowers are, and the next iteration of this talk will get better, right? With this, I'll invite Daniel as well as James on stage. We are done. Thank you. Thanks, everyone. Thank you. Thank you.